In part two, we learn more about where we source phosphorus globally and some aspects of losing phosphorus into the environment. We saw in part one that phosphorus used in fertilizers is dominantly sourced from phosphate rock, and the phosphate rock comes from mines. In the US, the annual consumption of mined phosphorus for fertilizers is around 5 million metric tons. Now, that number may not mean a lot to many, so let's make a comparison to something everyone knows is heavy, an aircraft carrier. An aircraft carrier weighs about 100,000 metric tons. 5 million metric tons is the equivalent to elemental phosphorus in weights equal to 50 aircraft carriers. That's heavy. And further, keep in mind that phosphorus is only one of the components in phosphorus fertilizers. There's a lot of other elements in there as well. So the total mass of fertilizers is much higher than this value just for the element phosphorus. Our known sources of phosphate rock deposits are isolated in specific areas of the world. In the US, for example, over 75% of the total US phosphate production comes from Florida and North Carolina. One implication of this is that phosphorus is available locally, but it must be transported across great distances for its use in agriculture elsewhere in the world. Finally, as it relates to sustainability, it should be noted that mined sources of phosphorus are non-renewable. Globally, we see a similar feature. That is, known phosphate deposits distributed in certain parts of the world, but not others. This distribution has some consequences and implications. For example, the cost of transporting solid phosphate rock or phosphorus fertilizers to places where it's used affects the economics and the prices. In addition, this brings in geopolitical factors, including but not limited to national policies and laws, international trade, and international conflicts. And before leaving this graph, let's look at the islands northeast of Australia, which are marked with X's, indicating island deposits, which allows us to introduce social factors into this discussion. Recall that heavy industrialization of phosphate fertilizers from phosphate rock starting back in the late 1930s and accelerating in the 1960s and 70s. Prior to that time, more easily accessible phosphate deposits were sought. One example is shown here, which highlights the island of Banaba. In the 1900s, the island of Banaba was identified as a potential source of phosphorus for fertilizers for use in other areas of the world. It was mined heavily in the early 20th century to the point of the island being rendered mostly inhabitable. In fact, most of the indigenous population of the island was relocated from their homeland. The stories of the people of Banaba are documented in this book authored by Katerina Martina Tewa, who is of Banaban descent and a professor in interdisciplinary Pacific Studies at Australian National University. Drawing from these lessons learned from history, as we advance phosphorus sustainability, we must be mindful of the social and ethical impacts on populations. More broadly, it's key to engage stakeholders in our processes and understand potential impacts on different groups and populations. Another modern day consequence of mining phosphorus is that some byproduct material is radioactive. Because the material is radioactive, it cannot be used for industrial or consumer products and cannot be disposed of in landfills. So this byproduct is stored indefinitely in large mounds or stacks, often topped with acidic water containing phosphorus and other chemicals. You can see an example of a stack on the left, located in close proximity to Tampa Bay in Florida. The byproduct is called phosphogypsum and results from the conversion of phosphate rock to phosphoric acid, a so-called beneficiation process in the mining industry. These stacks pose both immediate and long-term challenges to both humans and the environment. As one example shown here, a breach in a phosphogypsum stack in April of 2021 created a state of emergency in Florida. The concern was that an initial small leak in one of the retaining walls would steadily increase, causing an uncontrollable flood of the acidic water through communities. To remedy the immediate threat, the acidic water containing high concentrations of phosphorus was pumped into Tampa Bay over the course of days. And while this eliminated the immediate threat at hand, it placed a significant amount of phosphorus load into Tampa Bay. Which brings us to our next topic, which is the consequence of losing phosphorus to waters and a concept known as eutrophication. Eutrophication is a process in which the environment becomes enriched with nutrients such as nitrogen and phosphorus. In the mid 20th century, coinciding with events discussed earlier, such as increased population growth, mined phosphorus for fertilizers, and increased crop yields, there was a growth in eutrophication in inland waters such as lakes and rivers, often resulting in what are called harmful algal blooms. A harmful algal bloom is an event in which colonies of simple plants called algae grow out of control, producing toxic or harmful effects on humans, animals, and fish. Harmful algal blooms are often identifiable from the discoloration in the water caused from the pigments in the algae. You can see, for example, the characteristic green color of an algal bloom in one side of this image. To learn the source of algal blooms that were starting to plague inland waters, experiments were conducted in entire lakes in Canada starting in 1968. And this experiment from the so-called Lake 226 became famous. The lake was divided into two halves with an impermeable plastic curtain. While both sides of the lake were dosed with nitrogen and organic carbon, the half at the bottom was also dosed with phosphorus. And it's this side that shows the algal bloom. This knowledge nucleated and accelerated bans on phosphates in detergents in the 1970s, which helped to mitigate but not completely suppress observed algal blooms. Two other key contributors remain to eutrophication and harmful algal blooms in inland waters. These include human-induced phosphorus loadings from both wastewater and agricultural runoff. In fact, this image of a fish kill that resulted from a harmful algal bloom is from a few years ago in North Carolina. These observations reinforce the need to further improve our phosphorus management and reduce phosphorus pollution. Now we close this second part of the module in which we learned from where phosphorus is sourced and some consequences of releasing it to the environment.